So this last section is about kind of an applications and outlook, where is research going? So I wanted to present some of those use cases that I mentioned at the beginning. So, what do you do with all these dependencies that you've discovered? What kind of things can you do? Data cleaning, query optimization. I'll show you some examples. And then, as I said, if we get to it, more kinds of dependencies, at least hint at them, so it's not just only functional dependencies and inclusion dependencies. There's lots of more interesting stuff. I'll point to some technical challenges in terms of, where can we going, distributed computing, these kind of questions, and then some new directions at the end. Also maybe including text profiling that you had asked me about. Okay, so the first use case is query optimization. So we've written a survey this year, actually, on a survey on query optimization using metadata, using dependencies mostly. And so you can see by this, there are 58 optimization opportunities. There's a huge body of research out there. Sometimes it's called semantic query optimization as an area. And each of these boxes here is one trick or idea to optimize a query plan or query execution in a database, right? And this is using unique column combinations. This is for functional dependencies. This is for order dependencies, which I didn't mention. And this is for inclusion dependencies. And then here, these are joins, selections, sorting. What is this? I can't even read it. Ordering, I guess, etc. Set operations. So you can see there's a really huge amount of research. And I would go so far that almost none of it has entered commercial database systems. Why is that the case? What do you think? I mean, there's clearly a lot of research, and this goes back to, I think, the 70s or so, but still today, people are publishing on these ideas. So why is it not part of DB2 or Oracle or so? What do you think? Yeah? Data is too messy. Okay, so the admittance basically, a dependency is not, I can't find the proper dependencies because there are too many data errors. I mean, that's a good argument, absolutely. My counter argument would be, if we discover a functional dependency, it's valid, so I might as well use it for optimization. It's valid. For optimization, I don't really care if it's true or not, as long as it holds on the data, I'm okay with that. New technology, you're saying there's better ways to optimize, you don't need this stuff, queries are super fast anyway, in a sense, yeah? Maybe, I think there's also still sufficient amount of research on getting queries to run faster with other tricks, so I don't think that that's it. You can always just find more complicated queries and then need this. Yeah, go ahead.
Maybe we can relate it back to change, and because all these databases change quickly, it might be not static.
That's
on the other side, it might be good to identify data-driven because of that. If functional dependencies don't hold anymore and they used to.
So it's a very good answer, absolutely. So the data changes, and as soon as data changes, the dependencies are potentially no longer true. So I would need, and I'll get to that later, I would need incremental methods to detect them. So as data changes, which dependencies hold, which are invalid, which new dependencies have arisen. Exactly, so that's one part of the problem. What is the other problem?
Not user-friendly tricks, probably.
Say again?
I mean, probably it's not user-friendly tricks for...
Not user-friendly tricks. Some of them are super easy. There's not rocket science. Some is rocket science, but most of the stuff is really obvious, right? No, so the other problem is more mundane. I don't know all those dependencies, so I'd have to go discover them. And even if the data is static, we saw this might take hours. These are newer algorithms, right? So the old, state of the art was way too slow for significant data sets. So just simply the act of having to discover them and then storing them somewhere, you need a subsystem to do all that stuff. And that's why, I guess that's why this is not in mainstream database development. But my hope is now with new algorithms and cool new techniques, maybe it will start getting a foothold, right? But I will show you two very simple examples. Okay, this is a very simple query. Even if you don't know SQL, basically we're doing a grouping, right? So we're saying I'm interested in parts and descriptions and their average price, right? Group by part ID and their description for whatever reason. This is a grouping. And I know that the part ID determines the description, because it's an ID in this case, I guess, right? So it's a very trivial case. And that basically tells me that the grouping can be done simpler. I don't need to group by both. I can just group by one of them, because that already determines the other one. Right? It's a very simple thing. It's really simplify the query. It's not about adjusting the query plans. Really, the query can be simplified. I'll have to change this example. It's a non-obvious. Yeah, go ahead. Yeah. Incorrect. Oh boy. Okay, Divesh, tell me what's wrong with this.
The basic SQL requires that your select clause either include the group by and
Here the description can be. Yeah, right. You're right. No problem though. I'll just say max description. And I'll change that on the slides. Thank you. Very good point. Okay, good. Okay, but you get the idea. Here's another one. This is an inclusion dependency. So up there is a query. I'm interested about information for orders, and I have a join with the customer table, right? And but none of the customer attributes are actually in the output of the query. I'm just checking, is there a joint partner with the customer table, yes or no, right? But if I know that there's an inclusion dependency, then I don't need to do that check anymore, because I've done it in advance in a sense. So I can severely simplify this query, and it will be run much faster. These are very simple examples. You saw I had 56 other examples. Of course, I don't have slides for all of those, but these are often quite simple tricks, and they're very effective. Yeah, and I don't have a slide for this, but we did have one nice paper very recently of how to go about using these kind of ideas in query optimization. So I said earlier, you have to discover all the dependencies, store them somewhere, and then you can use them for optimization. So a master's student actually developed a system, which is a really nice idea. He said, here's a query. Which dependencies would I like to have to optimize only this particular query? And then we check those, and if they're true, we use that optimization trick. So we don't need all the dependencies. We only look for the ones that we need and validate those, which can usually be done very, very efficiently if you have proper index structures. And then we improve the query. And we tried this for TPCH benchmark, which is a very common benchmark, and many queries just simply run faster on the traditional data. It's a very, very simple trick. So anyway, so there's a whole bunch of research in query optimization using the results of data profiling. Okay, good. Next use case, data cleaning. I had alluded to this before. In general, the idea is the following. You discover not exact dependencies, but approximate dependencies, those that are almost but not quite true, okay? And then you verify their genuineness. You ask a user, in essence, is this a good dependency? Should it be true? Then you detect the violating records, and then you correct them, clean them, remove them, whatever you want to do with this. The interesting question, the interesting part, what I found interesting anyway, so this is what we've covered, right? There are heuristics about this, so there's some tricks you can do to help users rank them or so. We'll look into a few examples later on. What I found also interesting is this is also actually a problem, right? So given the dependencies, how can you efficiently find the errors? It's not easy. Especially if the dependencies are a little bit complicated. I mean, finding duplicates is easy, but finding violations of functional dependencies is already a little bit complicated. And there are more complicated denial constraints, like denial constraints, which are very complicated to formulate. And then finding the actual errors is a difficult task. So that's already a research paper, or research problem. And then correct the values is also not trivial. It's not obvious how to correct data errors in general. Right? I'll show you one nice little example that I took from Shuchu and Ihab and Paolo. This is in the context of the HoloClean system. They have some really nice basic intuition, in essence, right? Just to give you an idea of what the kind of thinking might be. So here the idea is, so you have this data set, tiny data set, right? And you think there should be a functional dependency zip code should determine the state. Again, I'm not sure if it's really true in the US, but let's say it should be true. So there's a violation here, right? So you have two same zip codes, but different states. So where's the error? What would you correct here? What would you change? without looking at, into a directory. Go ahead. It depends. Okay, there you go. Nice. Okay. But do you have any additional? I mean, depends on what?
We have to validate which, like if you highlight these two, check which one might be a violation, going which direction.
Okay, but let's say the direction is zip code determined state, right? So that's the direction of the dependency.
It might be a different way of missing data because it seems like it might just be the default way, exactly that one.
The 10,001? Yeah, maybe. Okay. So both are wrong, in essence, is what you're saying? Okay, could be. Absolutely. Okay. Yeah?
You already have a correct record with New Mexico in there.
Right.
There is some context there that you can use.
Right. So, well, we don't know if that one's correct, but at least, New Mexico, but it doesn't mean that there could be more than one zip code in New Mexico. But maybe New Mexico is wrong. So the point I'm trying to make here is any of the 4 involved values could be corrected, right? This one could be wrong. If you correct it, you're fine. This one could be wrong. This one could be wrong. This one could be wrong. Any change in any of the 4 values would lead to a correct or a non-violation of this functional dependency. We don't really know in general. Okay. So now here comes the trick. That if you have multiple dependencies, so for instance, you have a so-called denial constraint. I'm not going to explain this in too much detail, but the denial constraint might say that if 2 people are living in the same state and one has a higher employment level than the other, that person should also earn more money. That's a reasonable constraint. If you're at a higher level, you should earn more money, especially if you're in the same state. And there's a violation here, so Bob is at a higher level but earns less than Alice. So all power to Alice, but this is a violation at least of that particular constraint. So now, and again, it is true that any of these values could be the problem, right? Maybe the level is wrong of Alice, maybe the level of Bob is wrong, maybe the salary is wrong, maybe they don't live in that state, et cetera, et cetera. So any correction might be correct. But of course, now you can see an intuition might be to find the minimal repair. So if you correct that state value in New Mexico, you'd be solving both problems at the same time. Right? And if you have many violations, many dependencies, or many quality constraints, then one maybe reasonable approach is to find the minimal repairs. Right? And again, this is a research project. It's not easy to find them. It's not easy to determine them. But I think it's a kind of a neat idea of how to go about it. That doesn't guarantee you're doing the right thing, but it's at least an approach that might be even easier to verify because you don't have to show as many possible corrections to a user who has to validate them. Okay? So this is how you can use dependencies for cleaning, not just individual violations, but in their holistic view. That's why it's hollow clean. You can maybe do a better job in cleaning data. Okay, next use case is an obvious one. Anybody who's taken a database class has learned about functional dependencies, and you learn about them in the context of normalization. So who's had a database class and heard of normalization? Some of you. Okay, fine. So I said at the beginning of the tutorial, I said functional dependencies point to redundancy, right? So so the zip code determines the state. So I don't need to record the state. I just needed to record the zip code for a particular address. And then in a lookup table, let's say I say, okay, which zip code belongs to which state. I don't have to repeat the state every single time the same zip code appears, right? And normalization takes care of this by decomposing a table into 2 tables, one with all the addresses in this example, and one with the zip code and state lookup. Right? That's normalization. And there's a popular normal form, which is the Boyce-Codd normal form, BCNF, which is just a popular rule saying which kind of redundancies you're willing to admit and which ones you want to get rid of. I'll just keep it at that level. And to decide how to decompose tables, you need functional dependencies. And so you look at all your functional dependencies, you're saying, this one is something I want to decompose by, and say, I don't like this functional dependency, it violates the Boyce-Codd normal form, so I want to decompose my table. And so to do that properly, you need to know all those functional dependencies, right? And so this is exactly what we've been doing in the last hour. So the idea of this algorithm is you discover all the functional dependencies. I won't go into too much. You choose a key for the table you're looking at. The functional dependencies help you choose a key. You choose, through some heuristics, the one functional dependency that you don't like, semi-automatically, but it also works automatically, and then you decompose, okay? And then you do that again and again until you're satisfied, until all your tables are in this boycott normal form. Huh? The interesting part, I mean, the discovery we know about, this is difficult because you're have some heuristic choices, right? And we used some really, really simple heuristics, and they worked surprisingly well. So I'll show you. I mean, this is kind of simple stuff. What I like about this idea or this paper is how we evaluated it. So we took a popular schema. This is again the TPCH schema about products and orders and suppliers, et cetera, et cetera. So these are, 8 tables, that are provided, and they're already normalized to some degree. Not perfectly, but to some degree. What we did is we joined them all up into one humongous table, one big table, clearly with a lot of redundancy and a huge table. And then we ran our algorithm to normalize it, hoping that we get that schema back. Oops, sorry. Okay, and that's exactly what we did. And this is the result. So I've kind of color-coded it. So what happened, in essence, I mean, so first of all, on the first view, it looks pretty good. It's not flawless, but it's pretty good. So what happened at the top here is that, this is the original table, and then our algorithm normalized it even further because the TPCH schema is not in Boyce-Court normal form. So we went beyond what we would have hoped for, but we did identify that these things belong together, right? And then we did identify the part supplier and the part and the supplier, and they appeared in our result, right? Which is kind of nice. There's one actual mistake, if you will, which is this one here, you can see, right? So we have the region table with a name and a comment about the region, Africa, Asia, et cetera, and then the shipping priority went into that table. And it originally was in the order table. An order has a shipping priority, next day delivery or whatnot, right? But actually there's a dependency in TPC, in the schema, so the shipping priority is actually dependent on the region key. So all, I'm gonna say, African customers have 1-day delivery, all European customers have next week delivery, et cetera. So it's built in the data generation, so it's actually a flaw, if you will, of the benchmark, and in a sense we uncovered it here and did the right thing, saying, well, if shipping priority depends on the region key, then that's where it should go, into the region table. But we tested this for some other schemata, and it worked fairly nice. And it's kind of cool. You just automatically, whoop, there you have your normal form. And we actually did a product with SBB last year. SBB is the Swiss rail agency, and they have this problem all the time because they get data from all sorts of sources, all the different suppliers, even within the department, within the company, they get many different data sources, and they're supposed to do analytics on them. And now what they do is they use this algorithm to normalize the stuff that they get, and then identify which things are in this data. There's customers, there's locomotives, there's parts, there's rails, and if you normalize everything, then the individual parts kind of appear, and then you can integrate them easier. So this actually works pretty well. At least they're happy. Okay. So, a little bit more. I mentioned this earlier. This is about the genuineness of dependencies. So this is about inclusion dependencies. And I said earlier, inclusion dependency is a prerequisite for a foreign key. How do I fit 2 tables together? How can I join them? And an inclusion dependency is a prerequisite for a foreign key. But among the many inclusion dependencies that we find, again, often hundreds of thousands, right? How do we choose the right ones? This is what we want to do, the true foreign keys. And again, they're not intrinsic to the data, but they're defined by humans. No? Only a human can really do it. So instead of finding all things that are valid, we're trying to discover semantics, meaningful things, right? And so what I'll show you next is a few slides on one approach that we did, and then afterwards there's an approach that Divesh did, which is much better, at least according to their experiments. It's more elegant, that's for sure. Okay, so characterizing foreign keys. So we wanted to find, with this particular project, a set of features. How do foreign keys look in the real world? What do we expect if we look at a key and a foreign key and how they should join up. So just for everybody who's not too familiar with databases, think of key-foreign key relationship as the following. Think of it as an orders table. So think of Amazon and you order stuff, right? And each order is connected to a customer, obviously, right? So in the order table, there's going to be a customer key to know for which customer was this order. So that's a foreign key to the customer table. And the customer table has a primary key, the customer ID, and the order table has a foreign key, right? And so that's the kind of stuff we're looking for. And so in this intuition, first of all, every order has to have a customer. This is clear, right? Otherwise it doesn't make sense. So that's why it's an inclusion dependency, right? But furthermore, what do we expect? We kind of expect that, let's say, almost all customers have placed an order. Why else would they be customers? Right? And then we maybe expect that most customers have ordered a similar amount, between 1 and maybe 100 orders, not 1 million orders. And so there are different kinds of properties that we expect a foreign key to have. And I'll show you a few. And then we use those properties to say, okay, if all these hold to a certain degree, then we think this is really a foreign key. Right? So, for instance, if you have a potential foreign key, A referring to B, then probably the column A itself should not be the target of some other foreign keys. That would be an unusual situation, right? So we look at all the possible inclusion dependencies and say, okay, if this is if there's kind of this transitive inclusion dependency, this is a bit suspicious, right? Another example is we think A might be a foreign key for B, but we also think it might be a foreign key for C and D. Again, that's not how you model data, right? A foreign key refers to one column and not to multiple columns. So those can't all at the same time be foreign keys, at least not if you're a reasonable data modeler, right? But on the other hand, if you think A refers to B, and there's a bunch of other tables that also refer to B, that's a good sign. A primary key is often the target of many foreign keys. Right? So that's a kind of a positive feature to identify a foreign key. What else? If you look at this particular example, do you think A is a foreign key for B? Maybe not, right? It looks like, it's a coincidence. It's a constant column with lots of A's. Just because A appears in B doesn't make it a foreign key. Not very likely, right? And we also did stuff like this. So, the value lengths are different. So the characteristics of the two columns are different. Then maybe the coverage is interesting, right? So you have more than one value, you have a bunch of values, but they only cover a small part of B. That's also suspicious, right? That's probably not a foreign key. What else do we have? Out of range. So this would be a situation that we only cover, we have many different foreign keys, but they only cover the top half of the other table. That is, again, suspicious. And what else? And then, of course, you can look at column names, for instance, right? So if the names are similar, that's a good sign. You have a good data modeler that will give the foreign key a name that is similar to the primary key it's referring to. That's a very reasonable thing, right? And you might have typical suffixes. So foreign key might have a underscore key at the end, or number, or ID, and things like that. So those are also good hints, basically. Okay, so what did we do in this case? We put it all together, did a little bit of a machine learning, and were, successful in finding or identifying foreign keys. And then there's, I just briefly want to mention this paper here, again by Divesh and Mehui and lots of other great colleagues who kind of generalized many of these ideas and said, well, as you can see, actually you should probably talk about this slide, but I'll just briefly go over it. Basically saying, looking in particular at the value distributions. I said earlier, if one column is constant and the other one it has lots of different values, they're not drawn from the same distribution of values. They have a very different distribution, right? Or I said the range, one attribute covers only a small range from the other attribute. Again, they're not from the same distribution. So this was the intuition of this particular paper, and in a sense, generalizing many of the features that I showed you on the previous slides. This was the idea. And now, of course, the question is, how do I measure this thing? So where do I find this? Actually, I'll just go to the next slide here, right? So here was the neat idea of, okay, how do I find out if two attribute values are drawn from the same distribution or similar distribution? And the idea, actually, I want to show the next slide. I'll just jump to the next slide. So the idea is here that you need an order of the attributes, you rank, or the values, you rank them all, and then you measure the average rank difference between the values from, in this case, P and F. Those are the two attributes. And then you sum it all up. And the idea is if the sum is quite small, right? Most values in the second, in the dependent column are at the beginning of the distribution. If it's too large, then they're at the end of the distribution. And if it's just right, they are from the same, or sampled from the same overall set, right? And the experiments show that it works very well. Yeah? And I think you also added a little bit of a name matching as well, just to top it off. I didn't do this justice, I realize this. But anyway, this was the idea. Okay, so I showed you some use cases. Many of them revolved around schemata, basically saying, okay, how do I model it? How do I normalize it? How do I understand how tables work together? But this makes sense because data profiling extracts statements about the schema, right? About attributes and how they behave in essence, right? So, so we still have some sections. Actually, let me, I'll just show you one more dependency because it's kind of cool, the order dependencies, and then I'll jump to the rest. Okay, just bear with me. So I said there are many other kinds of dependencies. We just looked at three. What I really like are order dependencies. It's kind of a cool concept. It's an unusual one. You have to think about it a little while, but it can make sense. An order dependency basically says if I order my table according to one attribute, it is automatically ordered by the other attribute. Okay? So if I order by salary here, then it's also ordered by rank. Not the other way around. If I order by rank, it's not necessarily ordered by salary. So it's an order dependency. And they are not very frequent. If you look at any data set, you'll find one or two, not hundreds of thousands, right? So pretty strict, strict thing that we want to say. But once you have found them, you could, again, do some pretty cool query optimization, in particular if they involve order. So that's your table, that's your query. You're looking for employee names ordered by rank and salary. How can you improve this query? Easy question, I hope. So you're trying to give me all employee names ordered by rank and salary. Ordering by rank and salary meaning order them by rank, and in case of ties, order them by salary. This is the idea. So what can we do to simplify this query? So what I'm not sure if I quite got it, but it's actually quite simple. You don't have to order by rank. You just remove the rank. So it's just a simpler query, right? Because salary already orders them by rank automatically. That's what the dependency says. So a database system will be happy. It will say, okay, great. I don't have to do this complicated order by. I'll do a simpler version of it. Okay? This is a more difficult question for the database experts among you. What can I do here and why? So here I'm only ordering by rank. How could I change this query? Any ideas? It's not quite as obvious, but there's an idea. Go.
If you just order by salary instead, it should be the same.
Yes, so absolutely. So since salary already orders rank, I can just instead order by salary instead of by rank. Now you should ask yourself, well, why should I do that? What's the big deal, right? It's not a simpler query, but it actually might be a simpler query, for instance, if you have an index on salary but not on rank. Then that query will run much faster than the original one. So you don't always do this, but it might make sense to do this. Very, very simple optimizations. Okay. Good. So you can see there's a big world of stuff out there that you can look at, but I will take this opportunity to kind of jump towards the end of my presentation, and we'll talk about the tech stuff offline. Okay, during the meet and greet or whatever it's called. Okay, good. To conclude, 2 more slides. Of course, I have to thank all my collaborators in this area of data profiling. You can see many different names. These are all students in my PhD students in my group who have done some form or other of data profiling. So, the reason why I could show you all this great stuff is because these guys and girls did all the hard work. I specifically want to point out Thorsten Papenbrock. He's been, the main driver of this research. He also is, in a sense, the main creator of our Metanome repository. I mentioned this earlier, where we have all the data, all the algorithms, et cetera, et cetera. By now, it's a little bit outdated. It's an older Java version, and we really want to update it to a new, lift it up to a more modern level. But it is what it is. It works. Many people use it. So this might be worthwhile. And lots of great collaborators. Okay. So quick summary. Why is this not advancing? So summary and outlook. So what is going on at the moment? Currently, there's still a lot of work on efficiency. It's just getting faster algorithms, right? Every year there's a whole bunch of papers about this. New algorithms and this approximation or partial dependencies. So people are looking more and more into this. So not finding the exact solution, but finding dependencies that are almost true. Then there's a focus on semantics, so finding out which dependency is actually true, the genuineness, right? And then there's work on new kinds of problems, as I said, relaxed dependencies or new dependency types. If you open a database textbook under the term dependency, there's like 1 column full of different kinds of dependencies you could be looking for. And each one of them is a master thesis or a research paper. There's a lot of fun, although we always have to justify why are we interested in this, right? Just for the fun of it. And that's also interesting, but of course, use cases are important, right? And so where do I think the future is looking at? So efficiency is still also a future thing. There's not too much work on distributed data profiling. Why is that the case? Because pruning information has to be shared across nodes. Right? There's a lot of information that, if I know something is not true, I have to inform everybody else. So that's not very conducive to distributed processing. There is a little bit of work, but this is certainly an interesting problem. And then, as you mentioned earlier, dynamic data. There's a little bit of research there. What happens if data changes? The problem is I get a new tuple in my database. This could violate some of the dependencies that I thought were true. So suddenly something is not unique anymore. But it could give rise to new minimal functional dependencies, for instance, that I have to rediscover. So it's really a difficult problem. It's not just I look at the new tuple and I remove some stuff. New stuff could appear. So that's very difficult. Okay? And query optimization, I mentioned this. And then future focus on semantics. There's still a lot of research will be going on the genuineness and then using that for data cleaning, right? This is a lot of, this is the biggest potential. I think data quality, data cleaning, as you know, is one of the big problems. And then really new directions would be profiling RDF data. And there is work on that. It's not completely new. Profiling, general graph data, profiling text, hierarchical data, multimedia data, maybe. I don't know. So there's a whole world out there, and of course there is already work on that. Maybe it's not called data profiling, but it is analyzing graphs, analyzing trees for interesting properties, but maybe the communities can learn from one another. And with this, I am finally done. So thanks for sticking around. I hope some of the intuitions were interesting and looking forward to chatting with you later today.